Hello, everybody. Good morning, good afternoon, good evening for everybody. Today, there will be a talk given by Steffen Turkat on the Big Bang nucleosynthesis, or how to cook your elements quicker than instant noodles. Steffen is a very promising and exciting postdoctoral researcher from University of Padova. He is very happy about his research and very excited about everything. He did his PhD at the University of Dresden, where he worked mostly on the Big Bang nucleosynthesis reactions. As probably you will see during his talk, he's an expert on the detector characterization. He worked on the most background-free detector in probably all the Europe, which is a germanium detector that is located at the Felsenkeller laboratory, where he spent a lot of time during his PhD. It's a shallow laboratory where the background is reduced with respect to the surface. Now he's a postdoctoral researcher, as I said, at the University of Padova, and he's concentrating on preparing the setup for the carbon-12 measurement at the new ion beam facility at LNGS, which is the laboratory of Gran Sasso in Italy. So, Stefan, I leave you the room. You can start.
Jakub, what an introduction. Thanks a lot. Thank you also for the invitation to give a presentation here about one of my favorite topics, which is the Big Bang nucleosynthesis. So we are going back to the very, very early universe today, and I would like to talk about it from a nuclear astrophysics perspective. So of course, let's say the majority of time I'd like to spend to really talk about the Big Bang nucleosynthesis. Please interrupt me at any point. I mean, we're a community, we have different levels of knowledge and background regarding Big Bang nucleosynthesis. Probably there are some experts in here which could give at least the same presentation as me. And probably we have also some students in here who are not that familiar with it. So interrupt me at any point, please, and we can just discuss a little bit about stuff. First of all, I thought, okay, the majority will just be nuclear astrophysics perspective. Finally, I get the audience from astronomy and from cosmology to really just focus on the current experimental status of nuclear astrophysics regarding Big Bang nucleosynthesis. But actually, I changed the focus a little bit because it is a great opportunity to have the community of astronomy, cosmology, theoretical physicists, nuclear astrophysics physicists here to talk about the general scope of everything, because Big Bang nucleosynthesis actually enables or is an awesome topic to talk about if you want to talk about multidisciplinarity and so on and so on. So bear with me in the beginning. Yes, we will focus on Big Bang nucleosynthesis, but we will also talk about the early universe from a cosmological perspective. So we will dive into general relativity, we will dive into Friedmann equations just to see from this perspective how, in the end, everything comes together. So how is astronomy connected to cosmology, connected to nuclear astrophysics, connected to theoretical physics, for instance. And I'd like to start with a small quote. And this quote is, probably you all heard of it, "We are all made of stardust." I searched for quite some time to find the original author. I can imagine it was Carl Sagan, but more or less every science communicator who is working in the field of astrophysics somehow said this sentence somehow similar, that we are somehow made of stardust. So Jocelyn Bell Burnell, Neil deGrasse Tyson, Bill Nye the Science Guy, they all somehow said it in some kind of way that we are all made of stardust. I will leave this comment for a moment. We will jump back later to that one. Also, Brian Cox, probably you all know him. He gave a little bit more diverse interpretation of this famous quote, but we will come back later to that. We are all made of stardust. So what, or I'd like to ask you as the community, what are we actually made of? Okay, we are made of stardust, but since it's also, at least in Europe, late in the evening, I'd like to bring some enthusiasm also to you and ask you a question. So we start with a small quiz. And therefore, I'd like to ask you to pull out your cell phones, go to the webpage slido.com and enter the pin code 5467. You won't see anything there, but on the next slide, automatically on your cell phone, there should be a small question which appears. You don't have to join, it's anonymous, but I'd like to ask one question in the beginning. Before we dive into the origin of all the chemical elements with especially focus on Big Bang nucleosynthesis, let's stick to the Earth and ask the question, what are actually the 4 most abundant elements on our Earth, mass-wise, not abundance-wise, but really mass-wise, what contributes to our Earth? I will now open the question. So feel free to put in your most favorite or the 4 elements, the 4 chemical elements from whom you think they are most abundant on Earth regarding the mass fraction. So which 4 elements? You saw 4 of these elements, I just showed you the pie chart. 4 elements on the Earth are sufficient in order to describe more than 90% of the mass on Earth. 3 people already voted, so I don't know how many people are we, 26, so let's wait, probably, hopefully we reach 10. Thank you for participating. Probably 10 is already, oh, okay, yeah, let's wait a couple of seconds. So mass fraction, what are the 4 most abundant? And in the end, you have to scroll down probably a little bit to submit your entry. Wow, awesome participation, thanks a lot. Okay, 10 seconds, but then let's close this poll and have a look at the results. Thank you for participating. Let's have a look at your results. What are the 4 most abundant elements on Earth, mass fraction-wise? And let's say, in average, you say that carbon, hydrogen, oxygen, and nitrogen belong to the 4 most abundant elements on Earth regarding their mass. We have also helium, some people said iron and silicon, and this is basically everything. So let's agree as a community, our Earth consists of carbon, hydrogen, oxygen, neon. Wrong! Not wrong, but this has to be slightly adjusted because, of course, we have to take into account the entire Earth as an entire planet with all its core and with all its element in the inside. Carbon, hydrogen, oxygen, and nitrogen. Let's have a look at the result. Oxygen is true. There is no major amount of carbon, there's no major amount of hydrogen on Earth. The majority of the 4 elements to describe the mass on our Earth are iron, oxygen, silicon, magnesium. And this is fascinating. On the one hand, we probably all know what the universe is made of. So where is all the hydrogen? Where is all the helium? We could now have a separate presentation about this stuff. And also, this is not the first time I do this poll. I also thought similar things, but no, it's really just all the hydrogen or all the light elements during the formation of the Earth were just carried away by the solar winds. So in the outer parts of the solar system, you find all the gas planets with all the hydrogen and the helium content, which are similar in their amount as you would expect it. But here on Earth, it looks a little bit different. And this is, of course, interesting. Because if you now zoom out a little bit, and now let's try to leave the Earth and just have a larger scope on the entire picture, already if you have a look at the chemical composition of our entire solar system, this looks familiar. We have a majority of hydrogen and let's say 30% of helium. And if you even zoom out even further, the entire universe looks rather similar to the composition of our sun. So the majority of elements are hydrogen and helium. This chemical abundance we want to understand now within the next 35 minutes approximately. And of course, we could now dive into the most different fields of nuclear astrophysics. We could dive into all the people who do stellar evolution, who do we also had, I think I saw some heavy element people here for R process, S process, and so on. So of course, at least the nuclear astrophysics community knows this picture very well, the nuclei chart, and you see all the processes. So stellar nucleosynthesis, S process, R process, just the basic question, where do all the elements in the universe come from? We will focus on the very lower left part, on the Big Bang nucleosynthesis, on hydrogen, helium, lithium, the light elements, the production of the light elements. Yeah, so this is now what we want to focus on. And finally, we can actually start going into detail regarding Big Bang nucleosynthesis. So we leave all the other stuff behind. I also explain a little bit later why, but we will now dive into Big Bang nucleosynthesis. Just a brief introduction. You definitely all know, I think all of us are physicists, that we are living in an expanding universe. So we are living in a universe which grows and grows and grows, but the amount of matter and the amount of energy, of course, stays the same. Therefore, an intuitive assumption is that everything, or the energy density and the mass density, they should decrease over time. So if you have just a very rudimentary idea, or you want to understand how the universe in the past looked like, how did the early universe look like? Well, you have to squeeze everything together, distribute the entire mass and the entire energy on a smaller volume. Therefore, if you want to look back into the history, of course, the temperature rises, the energy density rises, the mass density rises. So if we have a look at the very, very early universe, we are dealing with a hot environment, especially in the first minutes. We are dealing here with, let's say, a couple of MeV, definitely some hundreds of keV. This is roughly now the energy regime we are talking about, which is, of course, nuclear physics energy regime, MEV, KeV, this is nuclear physics. So let's start from the beginning. As I promised, we also somehow have some analogy to nuclear, or to pasta, how's it called? Instant pasta or instant noodles. So how do we understand the early universe regarding nuclear physics perspective, regarding Big Bang nucleosynthesis? In the beginning, let's say we are now at the universe, we moved back in time, we are now, let's say, in a microsecond approximately, we're dealing with some energies of 150 MeV somehow in this regime. And either you go now to the grocery store and buy your yum soup, or you just have a look what is actually needed in order to start nucleosynthesis. It's both the same. You have a look what you have. In case of the Big Bang nucleosynthesis, you're dealing with protons and neutrons. So you have the quark-gluon plasma. Protons and neutrons decouple from or condensate out of the quark-gluon plasma approximately at 150 MeV. So you have stable protons and neutrons. In case of the yum soup, you can now have a look at the ingredients list. In case of the Big Bang nucleosynthesis, okay, the ingredients are clear. We have protons and we have neutrons. This is everything we can deal with. The question is now, how many protons and how many neutrons do we have? So basically the ingredients list. So what do we start with? Well, let's say in a time regime before 1 second, the picture is rather clear. We have the same amount of protons and neutrons. So we start with an abundance ratio of 1 to 1, 50-50. This is mainly due to just weak interactions, which preserves the equilibrium. Everything is in thermal equilibrium. So we have a 1-to-1 neutron to proton ratio in the beginning. The question now, okay, for the noodle soup, probably this question is not true, but at least for us, we have to ask the question, does this ratio stay the same? Do we have to take other effects into account to now really understand the full period of the first minutes of the universe, where the universe was able to produce heavier, or the first-lized elements out of the neutrons and the protons? And yes, at least the neutron to proton ratio, it depends on the mass ratio. You're in a thermal equilibrium, therefore, over time, this mass ratio leads definitely to a divergence, to a decrease of neutrons with respect to protons. We'll come to this also in a couple of seconds. Neutron lifetime, really important. Of course, you have free neutrons. They were just produced. Of course, they behave like normal free neutrons. They decay over time. So this also definitely has to be taken into account if we talk about the basic ingredients which are now needed in order to understand the Big Bang nucleosynthesis. Okay, so we have all the ingredients. We know how the ingredients behave over time. Now let's think about the last thing, which is the cooking process itself. So you can have a look at your recipe for the noodle soup, or you just ask the question in case of Big Bang nucleosynthesis, what is creating new elements? I think we can all agree on this has to somehow to deal with nuclear reactions. So you need to measure the nuclear reactions in order to understand the overall abundance after the Big Bang nucleosynthesis. And you also have to ask the question, is it possible to potentially dissociate elements? And yes, this will be a major topic of today's presentation, that we, of course, can also dissociate the elements during the early universe. You're dealing with MEV, KeV photons. Of course, if they have sufficient amount of energies, they can also dissociate the elements which were just produced. So we really have to take care of the baryon-to-photon ratio. This will be a crucial point of today's presentation. baryon-to-photon ratio. You can also express it just in terms of baryon density, so the amount of ordinary matter, let's call it. Okay, so the main idea is clear. In order to understand the entire Big Bang nucleosynthesis, we just need a couple of parameters, a couple of things which have to be measured. The Q value, or basically the mass difference of protons to neutrons, the neutron lifetime. We need the initial conditions that it's in thermal equilibrium, so we have a 1-to-1 ratio, and we need all the reaction channels, basically everything all the nuclear physicists and nuclear astrophysicists tried within the last 60 years, 70 years, to get an idea of what's the likelihood at a certain temperature that this reaction will take place or won't take place. Yeah, and the baryon-to-photon ratio, really important. Okay, let's now have a look at one of the most important and crucial figures of today, which is the abundance development over time. Probably I can just put on the laser pointer. Okay, so what you see here is the abundance given in absolute values, so 100%, with respect to the time in a logarithmic scale. This is important. As we said in the beginning, we are talking here about, let's say, 0.1 second to roughly 1 day. This is now the evolution of chemical elements during this period, Big Bang nucleosynthesis, within, let's say, the first day of the universe. And we start with protons and neutrons, as we just said. They just condense out of the quark-gluon plasma. We can also just quickly discuss what actually changes the ratio. We just roughly mentioned, okay, it has to do something with the Q value and it has to do something with the neutron lifetime. So they are in thermal equilibrium. You can also see here the formula. So the neutron to proton ratio decreases over time because the temperature decreases as well. We are just crossing exactly the Q value. The Q value is 1.3 MeV. So we are really crossing this Q value, and therefore we really see in thermal equilibrium this reduction in amount of neutrons with respect to protons. So this has to be now taken into account. Then at approximately 2 seconds, this freezes out approximately at a ratio of 1 to 6. So we have one neutron for 6 protons. And we have to also still think about what could now potentially happen. We are living in a hot environment back then. We are living at a couple of MeV. So of course, neutrons and protons, which are already existing, they would like to fuse together. They would like to undergo the D or the P plus N reaction and form deuterium. The main problem is we already talked about this baryon-to-photon ratio. And this baryon-to-photon ratio is approximately 10 to the minus 9. So there are approximately 10 to the 9 more photons with respect to baryons. So the photons have the majority in the early universe. Therefore, all the deuterium which would like to form, it's instantaneously dissociated, but just by the majority of photons which are just dissociating the deuterium. Therefore, of course, the energy density is also, or the energy is perfect for the production of deuterium. There are just 2 problems. On the one hand, it's dissociated all the time. On the second hand, unfortunately, deuterium is also the element, the stable element with the lowest binding energy. So it will be dissociated the longest. The other elements, they could already form. Their binding energy is way higher, so the photons would not have sufficient energy to dissociate them. But deuterium, unfortunately, has the lowest binding energy, 2 MeV, and is also, unfortunately, the first thing which can be built. You just have protons and neutrons. So the only thing like a Lego system is the first element you can build is deuterium. So this is why this entire deuterium curve here stays very low. As we said, okay, the neutron to proton ratio freezes out and nothing major happens until, let's say, 50, 60, 70 seconds, because we are still faced by this huge amount of photons which have sufficient energy to dissociate everything. We have to be a little bit careful because I just said the deuterium binding energy is 2 MeV. So everybody could now ask, hey, but at 2 MeV, if the photon energy is not sufficient enough, why doesn't deuterium instantaneously start to form? It cannot be dissociated anymore. But we always have to take into account that we're dealing with an entire Maxwell-Boltzmann distribution. And since the photons have the majority in the universe, even the high energetic tail of this Maxwell-Boltzmann distribution is just able to constantly photodissociate everything. So it really takes until the average amount of temperatures in the KeV, high KeV energy region, until even the high energetic part of this Maxwell-Boltzmann distribution is not able to photodissociate the deuterium. okay, now the interesting part starts, because now at a time, let's say around 10 seconds, 50 seconds, 60 seconds, we are slowly getting into a regime where finally the deuterium can be built. The first element can finally be built, or the first, let's say, compound element can be built, which is deuterium. So as soon as the universe sufficiently cooled down, finally the deuterium can kick in. It is not photodissociated anymore. All the elements, other elements you can see here in green, helium-3, tritium, helium-4, they waited desperately for deuterium to be formed because they could have been built already way earlier. Their binding energy is way higher. The only problem was that their seed was missing, the deuterium. This is what we call in nuclear or in Big Bang nucleosynthesis, the so-called deuterium bottleneck. Basically, the entire universe had to wait for this damn deuterium to be built and not to be dissociated anymore. And the rest of the story is just a rather simple scheme of reactions which need to be understood in order to understand the entire picture, how the chemical evolution will look at the end. We won't go now into detail, but roughly in the end, the deuterium is formed. Therefore, as soon as deuterium is formed, also helium-3, helium-4, and tritium can be formed. And as soon as you have these three nuclei, you can also go to, let's say, higher elements. We're just facing one problem here. There's a major gap here. At A equals 5, there is no stable nucleus. Therefore, you really have to do something like helium-3 plus helium-4 or tritium plus helium-4. Therefore, if you have a look at the abundance of lithium-7, beryllium-7, lithium-6, they are, let's call it more or less already negligible. We do not need to talk about carbon-12 in the early universe. We can stop right at mentioning the small traces of beryllium-7, lithium-7, lithium-6, because we first of all had to produce the seeds for them, and even this took a sufficient amount of time. So after, let's say, 3 minutes. Some people say 3 minutes, some people say 5 minutes. Let's agree on roughly after 3 minutes, the majority of elements was already formed. Big Bang nucleosynthesis stops because the energy now is not sufficient anymore to do nuclear fusion. In the beginning, it was too large and just the photons photo-dissociated everything. At the end, the energy is not sufficient anymore. You cannot overcome each other's Coulomb barrier anymore. Therefore, you have a very narrow time window where nuclear physics in the early universe is actually relevant. Just let's say from the first second, we can also say later, to the third minute. 180 seconds, and the entire universe had to invest in this time in order to cook their elements appropriately for the next 14 billion years. Because afterwards, the universe itself never had sufficient energy anymore at any time intrinsically to overcome the nuclei's Coulomb barrier. Of course, you can have then gravitational effects and star formation and so on, but the universe itself, intrinsically, after 3 minutes, it was gone. The energy density was just low. I also presented a small, or I have here a small simulation just to really focus on this deuterium bottleneck, because this is really crucial also for the upcoming part of the presentation. Where you really see that everybody had to wait for deuterium, and as soon as deuterium kicks in, everyone else will also join. So you can see here the abundance with respect to the nuclei chart, and we can now play this. In the beginning, you see you just have protons and neutrons. Deuterium, nothing happens, but as soon as deuterium kicks in and gets lighter, pam, all the seeds for then the heavy elements are also produced. So this is basically just a graphic representation of this deuterium bottleneck, but it really illustrates how you need this deuterium to then finally kick in the other elements. This is basically it. From a nuclear physics perspective, of course, we need to understand the cross sections. Of course, we need to understand the entire underlying nuclear physics, but this is a task which is more or less understood. So in the end, we can summarize. This was the universe after 3 minutes. It took 3 minutes, and this is now one of the main messages. Hey, it's quicker than instant noodles, because instant noodles probably also take 5 minutes. But the universe just took 3 minutes, and this is now the chemical abundance of, or the abundance of chemical elements after 3 minutes. We have 75% hydrogen, 25% helium, and that's it. Minority, less than 1%, also other stuff, but let's say negligible. Let's compare that once again to the universe after 14 billion years. This looks rather similar. And this is now also an important point. I have to be a little bit careful here, but let's agree on the statement. On a linear scale, if you just have a look at the pie chart, no star, no supernova, no neutron star merger, no other astronomical big event was able to fundamentally change something on the chemical abundance, which was already existing after 3 minutes. If you, on a linear scale, on a pie chart, want to understand how the chemical evolution of the universe we still have today, how this picture was made, you just have to understand the first 3 minutes. This is a rather risky statement because, of course, this is just true on a linear scale and on an absolute scale. And of course, all the other elements, as soon as you kick in the logarithm, of course, the majority of things which need to be understood, all the other R process, S process, stellar fusion processes, and so on, of course, super relevant, but just on a linear scale, you need to understand Big Bang nucleosynthesis. And this brings me back to my, I don't know, third slide, I think, where we just said, hey, we are made of stardust. And let's have a look what we are actually made of. I could now start another question, but I think let's go to the more important stuff. We as a human, the majority, I have to be a little bit careful because we are now talking not about mass, but really about the amount of particles. Humans are made of hydrogen. 63% of the atoms in our body are hydrogen. There's 1/4 oxygen, carbon, nitrogen, and so on. So from just the understanding of the amount of atoms in the body, you can say the majority is hydrogen. We just learned that hydrogen, these are the same atoms or the same nuclei which already existed after 3 minutes. So I don't want to doubt or question now this famous statement that we are made of stardust. I just want to highlight and emphasize the point that we could actually also just say, hey, we actually made of Big Bang nucleosynthesis dust. Yes, of course, also stardust, but the majority of the atoms in your body already existed after 3 minutes. Yeah, so just take this into account whenever someone tells you, hey, you're made of stardust. Add, please, yes, but also there was a lot of Big Bang nucleosynthesis involved in the creation of me as a body and my atoms I'm composed of. That's it. This is basically just now the summary for Big Bang nucleosynthesis. We understood we need some basic ingredients. We understood what needs to be measured. Neutron lifetime, Q value, more or less done. Nuclear reactions, and we have one important parameter, which is the baryon-to-photon ratio. We can also go back. I'd like to go back. Excuse me for that. Just to get an idea of the baryon-to-photon ratio. Baryon-to-photon ratio means if the baryon-to-photon ratio increases, so we have less photons available, then the Big Bang nucleosynthesis, the deuterium bottleneck, the Big Bang nucleosynthesis could already have started earlier because deuterium would not have been dissociated at these times because we don't have the photons anymore. So this baryon-to-photon ratio is a crucial parameter in order to say how much of the basic ingredients, hydrogen, or protons, neutrons, deuterium, can effectively be fused into helium-4. So as soon as we change this parameter, this will have a drastic change on the final output. As soon as we increase the baryon-to-photon ratio, we have less photons, and the entire Big Bang nucleosynthesis has more time. We don't just have this tiny amount, we have a longer period because deuterium is not dissociated. Therefore, we will effectively reduce the amount of deuterium and increase the amount of helium-4 whenever we increase the baryon-to-photon ratio. Okay. Okay, this was it. Basically, we understood now basic Big Bang nucleosynthesis. I'd like to paint now a larger picture. I'd like to quickly dive into cosmology from the cosmological perspective in order to understand this parameter, the baryon-to-photon ratio, because there we can really all agree on that we are all somehow dealing with this baryon-to-photon ratio, everybody from a different perspective, but this is one of these parameters which unifies us all as a community, astronomers, cosmologists, theoretical physicists, nuclear astrophysicists, and so on. And therefore we can also probe each other, which will be one of the main parts in the end. What would be an introduction to cosmology if we don't start by Einstein? Just very quickly. Einstein wrote his general relativity. You can see it over here. We won't go into detail. The main thing is just, this is a quite complex formula. So you have 10 coupled, nonlinear, partial, retarded differential equations of second order. No one is able to solve them. You need to introduce some symmetries. In case of, don't know, you could, for instance, now, if you want to consider black holes, you could now just add the symmetry. I'm dealing with a homogeneous, non-charged, non-rotating sphere, and then you would get some kind of metric, the Schwarzschild metric, to describe black holes. In case of cosmology, we have another symmetry, which we have to throw onto the general relativity, which is called the cosmologic principle. The cosmologic principle is very easy. It just says, hey, whatever I'm dealing with, everything is homogeneously and isotropically distributed. This is the cosmological principle, and as soon as you throw this onto your general relativity, you get the so-called Friedmann-Lemaitre-Robertson-Walker metric. I don't want to go into detail, but it is important for the upcoming part because the Friedmann equations, which are shown here, the basic equations, these are two equations which describe the evolution of our entire universe. The so-called Friedmann equations, they're just the result of the Einstein field equations of general relativity for the Friedmann-Lemaitre-Robertson-Walker metric. So long story short, doesn't matter if you did not listen for the first part, these are the equations which are describing the entire evolution of our universe under the assumption of the cosmological principle. So let's have a look at it. So you have the Hubble constant, so it describes the expansion velocity. And what does it depend on? So now Einstein, Friedmann, whatever, they all agreed on, hey, it depends on the total mass or the total energy density rho. There are also some other things, we won't go into detail, but let's say the key parameter in order to understand the history, the current state and the future of our universe is the total energy density. The evolution of the entire universe basically only depends on its entire energy density. So we as a community in the 50s, 60s, I'm not an expert on the history of physics, we said, okay, challenge accepted. If the entire history of the universe and the future of the universe depends on the total energy density, let's measure it. Let's design the most complex experiments humankind ever saw in order to understand what the entire energy density of the universe consists of. And what we came up with after
Sorry, Steffen,
decades.
this is
Yes.
just to say that you have still 12 minutes. So, and there is
Yeah.
a question. So if you
Oh,
want
yeah.
to, okay, so someone is asking, can you confirm decreasing baryon-proton ratio will have changed the composition of our universe, with universe having more heavier elements?
Sorry, once again.
So basically, decreasing baryon-proton ratio would have changed the composition of our universe, with universe having more heavier elements.
Yes, we will come to this since we don't have so much time. Exactly this question will be answered in a couple of slides. I'll come back to this.
Okay, please go ahead.
So what we came up with now is this plot. The pie chart, what is our universe made of? It is mainly made of dark energy, dark matter, and just a small amount of ordinary matter. This is the baryonic matter density, 5%. Or we could also convert this number now to the baryon-to-photon ratio. So we have a precise understanding. And I won't go into detail why we have this understanding, because unfortunately we don't have the time for that. There are several people who dedicated their lives to get this pie chart of what our universe is actually made of. Long story short, they all agree on more or less the same. There are no major discrepancies. We all agree on, if you have a look at the amount of dark energy with respect to the amount of dark matter, we agree on, let's say the majority is dark energy, 70%, and the entire matter density is approximately, let's say, 30%. One of the most crucial experiments in order to understand that we know what the amount of matter, we know what the amount of dark matter is in the universe. One of the most precise experiments which was ever done was the investigation of the so-called cosmic microwave background. So just one slide, but also just to emphasize the idea of the cosmic microwave background. Probably we have the astronomers here in the audience, therefore I don't have to go into detail. Probably you all heard of it. You can just measure the microwave, which is now microwave photons, which were emitted, let's say 380,000 years after the Big Bang, because you have the recombination of freely moving electrons and atoms. They recombine and therefore they emit exactly the energy you would need in order to dissociate them. This is called the cosmic microwave background. You can also measure the temperature fluctuations across this entire sphere, you can observe with respect to the, let's say, more or less the multipole, so with respect to the spherical distances, and you get this awesome picture measured by the Planck satellite. The most important thing which I want to emphasize here is this awesome publication, which shows you how you actually get from this so-called power spectrum of the cosmic microwave background to the idea of how much dark matter and how much dark energy do we actually have. So you see, for instance, for the dark, let's concentrate on the baryons, because this is the stuff we want to talk about. You see that as soon as you change the baryon density in the universe, you would drastically change this power spectrum with respect to the first peak, or the first peak with respect to the second peak. So as soon as you precisely measure the cosmic microwave background, you already from this measurement know the baryonic density of the universe, because the entire cosmic microwave background would look completely different if you change the baryon, just the baryon density. With the dark matter, it looks even different, so you can even distinguish baryon density from dark matter density. Awesome publication, I can highly recommend it, at least for non-experts who at least want to understand what the cosmic microwave background is. So long story short, with certain experiments, for instance, the Planck satellite mission, we are able to precisely determine the baryonic density in the universe. Let's bring everything together. So let's now try to paint the entire picture. We talked about the importance of the baryon-to-photon ratio, or the baryon density, from the perspective of nuclear astrophysics. This is the one question we will just answer in a couple of seconds. We also understood that other experiments like the Planck satellite is able to precisely determine, based on the shape of the power spectrum, we are able to determine the amount of baryons we have in the universe, roughly 5% of the total energy density in the universe, roughly 5%. So let's paint the entire picture and let's put everything together, which we just found out from astronomy, cosmology, theoretical physics, and nuclear astrophysics. This is the so-called cosmic concordance plot, which is shown here is the observed abundance from astronomers for helium-4, shown here in violet, for deuterium with respect to hydrogen, for helium-3 with respect to hydrogen, and for lithium-7 with respect to hydrogen. You now see exactly the question which was raised earlier. How does the baryon density influence the overall ratio of the elements? And yes, we can see it here perfectly, because these are the theoretical curves by us, the nuclear astrophysicists or the nuclear physicists. So how would the baryon-to-photon ratio or the baryon density, they are just equivalent, you can just transform one into each other, how do they theoretically influence the overall outcome after the Big Bang nucleosynthesis? And you can see exactly what we said. As soon as you increase the baryon-to-photon ratio, so you decrease the amount of photons or you increase the amount of baryons, Big Bang nucleosynthesis has a longer window in order to conduct their reactions, in order to fulfill its duty. And its duty is to transform the light elements into heavy elements. And everything it can do is just transform protons, neutrons, and deuterium into helium-4. So you see that deuterium will decrease if you have more time, because the baryon-to-photon ratio increases, you have less photons, deuterium bottleneck moves to the left, you have effectively a larger window, the amount of deuterium decreases. Also helium-3 as a seed decreases. Helium-4 increases, because this is what the Big Bang nucleosynthesis urges to do in its early stages. It wants to produce helium-4 because it is so stable. For lithium-7, the picture is a little bit more difficult, but we skip that now. So now let's put everything together. This is us, the nuclear physicists. We draw these lines. You see, we have some problems still with lithium-7. We're working on that. But in the end, the picture is more or less precise. Let's now add the astronomical observations, because we as a nuclear physicist, we can of course go to the astronomers and ask, hey, can you have a look at some clouds or at some other environment where you think not a lot of nucleosynthesis took place? And just measure the amount of deuterium and measure the amount of helium-4 and measure the amount of lithium-7 and tell us what you see, because then we can work together. We can take your results, you measure the helium-4 content or the helium-4 abundance, and then we can take our curve from nuclear physics in order to measure or determine the baryon density or the baryon-to-photon ratio. Let's do that. And already this is an amazing result. Astronomers were able to determine helium-4 abundance, or they were, let's say, brave enough in order to give us the numbers where they think in these environments not a lot of nucleosynthesis happened, and therefore we can somehow say it is the primordial abundance which we give you for helium-4, for deuterium, and for lithium-7. They are orders of magnitude apart from each other. We are talking here about 25% and 10 to the 10%, 10 to the minus 10%, or 10 to the minus 8%. And still, they show exactly more or less the same value. They all point towards a baryon density of approximately, let's say, baryon density parameter of 0.22. H squared is 0.5. Therefore, this is exactly 0.22 divided by 0.5. This is exactly of 5%. This is the amount of matter we have in the universe based on astronomy and nuclear physics. We can put it in here. This is now the Big Bang nucleosynthesis result. Of course, the majority of, or let's say the precision, comes from comes from the deuterium abundance because astronomers are very precisely able to tell the deuterium abundance. It's more difficult to give a value for helium-4. It's more difficult to give a value for lithium-7. Therefore, also the projection onto the x-axis, the determination of the baryon density is more complex. Therefore, of course, the entire precision is based on, let's say, or if you build the average of these three values, they will just be dominated by the deuterium abundance. We have a precise value. We did our job, and now we cannot only say, hey, all the astronomers, they come up with the same result in agreement with nuclear physics, but we can also now compare this entire picture of these two entirely different or independently working fields. We can compare this now to the cosmic microwave background results. As we said, from the power spectrum, you can just not easily, it's a huge effort, but you can, as we saw from the peak ratio, see what is actually the baryon-to-photon ratio. Let's put it in here. And this is one of the most remarkable results, which we as a community should use in order to, whenever we are faced with the fact, hey, with the question, are you doubting that, why should I believe you that we had a Big Bang? Why should we believe you that everything you're doing is correct? We have four with theoretical physics, entirely independent fields who come up with the same exact cosmological parameter in order to describe our universe. This is a huge effort, this is a huge success, and there we should also be proud that we all end up with the same value. Of course, we are still dealing with some problems, but this is a remarkable achievement. I won't go into detail. Of course, I would love now to talk about the achievements, at least by the lunar collaboration and the nuclear astrophysicists, in order to accomplish this result. Unfortunately, I don't have the time, bear with me, but let's say we all did a good job. Or let's say the elderly generation did an awesome job, and now we can not take over, but we can improve these results and test to do even more precise experiments and understand, is there new physics? We are still able to be more precise, especially from the nuclear physics point of view. So now let's more or less come to the summary. We are able to describe from the most different fields of physics, astronomy, cosmology, not the most different, but entirely independently working fields, theoretical physics, nuclear astrophysics. We are able to paint a coherent picture with orders of magnitude possibilities. We are able to focus on the same value, the baryon-to-photon ratio, the amount of baryons of ordinary matter we have in the universe is approximately 5%. This is a huge success. However, I also took the time just to have a look at recent papers of theoretical physicists, of astronomers, of cosmologists in order to see what's actually currently limiting further precision. Of course, this is not a blame of one community to the next community, but really just to get an idea of what the community, as far as I understand from the publications, currently thinks. So regarding astronomy, people are still saying, okay, hey, we are still dealing with this huge problem, which we call the lithium-7 problem. I did not go too much into detail here, but you see, regarding lithium-7, we still currently get a baryon-to-photon ratio, which is not entirely in agreement with all the other results from deuterium and helium-4. This is what we call the lithium-7 problem. I don't want to put much emphasis on this because this is an unsolved problem. Already by putting this into a yellow color and somehow blaming the astronomers there, it's their fault. I just want to reflect what's written, for instance, in the particle data group, where they write, okay, the there is mounting evidence that effects of stellar depletion cannot be ignored, so that the stellar abundances of lithium may not correspond to the primordial abundance. So I don't want to say it's nuclear physics' fault. It's probably could even lead to new physics or physics behind the standard model, or it is the astronomer's fault. But more or less, I have the feeling as a young scientist that the majority of the community currently points towards problem in the astronomical determination, which is rather complex, which is extremely complex. But currently, most of the nuclear physics problems are ruled out. Let's say additional resonances, which were never seen before, or something like that. Nuclear physics has their own problems. We are still dealing also with the fact that people say, so the majority of uncertainty, in order to be more precise, in order to narrow down this pink window even further, the majority is currently, or the majority of the community is currently saying, hey guys and girls, you need to concentrate on the DDN and DDP reaction. The main part of the error budget is due to DDP and DDN. DDP and DDN, wherever you look, currently this is regarding nuclear physics. The most important thing in order to compare our big fields we are working in even more precisely, to have a look, hey, do we all agree, or is there some new physics involved? And I want to close with two last comments, which is more or less some general statements for all of us. So on the one hand, we think that a closer collaboration among different groups in assessing a common understanding and quantifying the theoretical primordial deuterium abundance uncertainty would be quite important and desirable. Of course, we should, as a community, all work together and compare each other. And I could also highly recommend this summary. Just read the entire summary, because they also point towards different fields and who has to work on what in order to combine these different fields even better. And to say a free interpretation of this summary of this publication, we also need to urge for correctness and not for precision. So sometimes it's better to have a correct result than to claim the most precise result and beat the others. Thank you for your attention.